Okay, so this morning I want to take an application of these term symbols and the splitting of atomic spectra. And I put in this set of notes, just this lecture a couple of years ago, kind of when I discovered how relevant this was in informing us about our universe. I thought this was really cool. How many people have heard of the red shift of the stars in the universe? Do you really know what that means? So today you're going to understand what they're talking about in terms of the red shift, okay? And then we're also going to look to see how the atomic spectra has helped us understand that red shift and what it means in terms for the vastness of our universe and how it's expanding and so on. So this is applying atomic spectroscopy to the stars. So I think it's kind of an interesting lecture and an interesting topic. So I want to put this in for your edification. So if we take a spectrometer and we aim it at our sun, we see the black body radiation curve. This would be, that curve that is due to the hot object. Very hot, okay? It's in the visible range. If you look at the Planck distribution law for the black body radiator, you could come up with a temperature and so on. And so we could do that. We could apply this to the temperature of the light coming out of the sun and get some sort of solar temperature rated for that. We use that same kind of idea, that black body radiation curve, to rate our light bulbs and so on, to produce a certain color temperature. You can go to Home Depot and see there's a little light bulb display, and it says soft white and warm and daylight and so on. And you punch the little buttons, and they go from like and it even has the temperature, like 3,000 Kelvin, 4,000 Kelvin, 5,000 Kelvin. And you see as they get hotter, they get more blue light and so on. But if you look closely at that spectrum, you see dips. So you see absorbed light. You see some dark bands called Fraunhofer lines. Okay, and some of these are understandable. The sunlight's coming through our atmosphere, and so we see dips from oxygen. And so the oxygen of our atmosphere is absorbing some of that sunlight that comes into our spectrometer. We even see some hydrogen. Water is very abundant on our planet, so maybe as that oxygen gets higher in the atmosphere, it gets ionized by UV light from the sun and produces some hydrogen and produces some oxygen atoms. And we see the atomic spectra absorptions of these elements. But then if we keep taking this idea that this is the spectrum of our atmosphere, we run into a problem because of these D lines here. These D lines here are sodium. And yes, there's a lot of sodium in our Earth, but it's probably not in our atmosphere. Okay? So this is something else that's going on. And also iron. Oh my goodness. We have iron in our atmosphere? No, this is telling us something else is happening. So we could like wave our hands and say this hydrogen is from our water, but it's really not. It's from this other body that light is traveling through. So we have our sun, and it is a nuclear fusion furnace. It has reached the size of mass that the gravity is pulling all of these particles, originally mostly hydrogen, together. And you think, well, hydrogen doesn't weigh that much. But if you have enough hydrogen, the hydrogen that's in the middle is getting slammed by hydrogen that's further out. And that density is packing it closer and closer together to where the repulsion of the nucleus is not enough to keep those hydrogen nuclei apart. And so if they get pressed at a high enough density, they can fuse and make helium. And then that raises the temperature dramatically, which increases the kinetic energy of all of those other particles, which then slam into each other more often, and they overcome the repulsion of the protons, and they fuse to helium. And so then you start creating this fusion furnace, and then it lights. So like that star then lights up. So we can look around the universe and we can find sort of dense clouds of dust. A lot of those clouds of dust are light elements like hydrogen and so on. A lot of them are heavy elements like iron from stars that have blown apart. Okay. But our sun has been stable for quite a while, and it's this nuclear furnace. But still, if you're closer to the outside and you get hit by gamma rays and so on, you might escape and go a little bit further out than that hot visible part of the sun. And then you have this cloud of gases that have been ejected from the sun, but are still heavy enough that they're sort of stuck in the sun's gravitational pull. And so that light that is emitted from the hot sun hits these cool atoms like sodium that have been ejected from the sun but are still trapped by the sun's gravitational pull. And so there's this cloud of gaseous atoms, heavy atoms like iron and sodium, that are out there that are in their ground states and can absorb the light as the light goes through that cloud. And so we're getting a spectrum of our sun when we shine our spectrometer at it. It's really pretty cool. And so then that light that comes to us is missing some of the yellow light. You see the picture. And so that sodium has absorbed some of the yellow frequencies of light or yellow wavelengths, and we see them as these dark dips in the spectrum that we get on our spectrometer. So that's pretty neat. We're actually able to measure the atmosphere of our sun just by shining a spectrometer at it. We have the source, we have the sample, we have the detector, but they're really far apart. So 8 light minutes apart. So it takes 8 minutes for the light of the sun to reach us. That's a long way. Okay, and so you can take the speed of light and figure out what the miles is. And so the light, the source is the sun, the sample is that cloud, sodium, iron, and so on that are being ejected from the sun, and our detector is here in our lab. And that spectrum here was collected from my office. Like I just stuck my fiber optic spectrometer, the USB spectrometer, at my sun, I didn't point it straight at the sun. I kind of had a reflection on my blinds, and I pointed it at that, and that was enough to get this spectrum. And then, so there's spectral differences. We've been doing stellar spectroscopy for, probably 100 years now. And you can look in all different regions. We've put up satellites that measure all of these different ranges. So we'll put a satellite so that we can definitely get rid of our atmospheric interferences. We can put a satellite outside our atmosphere and look at different stars and so on. The Hubble telescope does that, but we also have X-ray observers and infrared satellites that look at different regions of the spectrum, even microwave. And so you can see if we're looking at the same galaxy, which is a close by galaxy, I believe this is Andromeda. The number is NGC 1512. I have to go and see what name we've given that. But you can see all the different spectral differences. And you see, of course, in the infrared, you get most of the light, okay? But in the UV, you get very little. But you still can see certain objects that are emitting quite a bit of UV. So this is what's going on. This is our standard cosmology model. And when we talk about the expansion of the universe, we're talking about this piece right here. Notice it's not flat. It's not a flat cylinder. Now, what is this being portrayed here? We can't really display 4 dimensions. We work in 4 dimensions all the time. You have 3 spatial dimensions, and you have a 4th dimension time. And so we can't show that 4th dimension time without a video, okay? If we show a video, then that's a 4-dimensional thing. You can see the space change as time goes by. But if we want to show a static image, we just have to take away one of the spatial dimensions. And so each time slice is a disk here. And so we would be in this current disk right here of our universe with just one of the spatial dimensions removed, okay? And so each one of these disks represents the volume of our universe, and you see that volume is increasing as it goes on. And it's also not really linear. It looks like it's accelerating. And so as time goes by, this universe is accelerating in its expansion. Now, this is sort of space itself. The dimensions of space is expanding. What that means is difficult for me to understand. Like the distance between 2 objects is expanding. It's not that the objects are just expanding like a gas into a fixed space. Like this room, for all our purposes, is the same dimensions as it was yesterday, but not really. Like space is expanding. Okay, now it's immeasurable in this room, but when we're looking at large distances away, like, megaparsecs away, we can measure the difference in space, okay? Now, if we go back here in time, we see a time when the galaxies were much closer together, and we see a time when they were really close together, and then we see a time when there was really no discernible galaxies, and and this was then before really we had chemistry and nuclei and so on. They called this the dark region. And then we had this afterglow, or the cosmic microwave background radiation. So cosmic, I'll go ahead and write this out since it's a current topic. Cosmic background.
It's nice that they've been able to narrow that down to 380,000 years. Right?
Yeah, that's right. Cosmic background radiation. And they put a black body irradiator on that, like the curve, the black body curve, and it's just like 4 Kelvin, okay? But it's not 0, okay? And that was a big deal. They said, wow, this is the sort of the radiation left over from that initial expansion of the universe, and it has cooled over time, and it's not at absolute 0, but it's cooled down to about 4 Kelvin. Now they have the models that they've modeled this sort of expansion and so on, and they said it shouldn't be 0 because of the way it's expanding now, and it should be less than a certain number. I don't know the details, but it was right in the window that sort of confirmed their model. That was a huge discovery, this cosmic background radiation. It's in the microwave region. But then this right here, this initial inflation, this is the thing that's most curious to everybody that studies this inflation, because it is expanding faster than physics allows. This initial inflation is a huge question mark, because it's faster than the speed of light. It happens not quite instantaneously, but almost. And so that is a big question mark, okay? And so they have put here quantum fluctuations as this idea of what could have started the universe. But that's a big question. What is a quantum fluctuation? Well, over here in our little disk of space, if 2 gamma rays are coming at each other and they happen to hit, we get the opposite of annihilation. We get an electron and a positron. Now, these are oppositely charged electrons, and I know that kind of breaks your brain because electrons are negative, right? But positrons are positive. Same mass, same spin, all these different kinds of things. It's a positive electron. And because they're attracted to each other, they will circle back and they will hit each other again and annihilate and go back to energy. So this is a mass to energy conversion. And it follows that equation, E equals mc squared, okay? So the mass and the energy are related by the speed of light. And we see this today. We see evidence of this positron and electron matter-antimatter pair and its relation to light. And they call them quantum fluctuations. They blink in and out of existence, if you will. But that word existence is the thing that's a problem, okay? As if matter exists, but light doesn't, right? They say electrons and positrons pop into existence from nothing. But that's not true, is it? There's light. So you're getting mass from non-mass, but you're not getting something from nothing, okay? And so that's why they put this quantum fluctuations down here. We observe this here, and they say, oh, we get something from nothing all the time. So that must be where the universe came from. But light is not nothing. It does appear that this universe and everything, even before this spot, there was no light and there was no time either. The time is sort of this change in entropy. And so time is tied to entropy. If you don't have matter, if you don't have energy states, if you don't have anything, you don't even have entropy, okay? And so this seems to be the beginning of everything. Now, they want to call it quantum fluctuations. That's not so clear that applies. And so that's why this is such an interesting question. So what caused this? What was this, okay? We've spent 100 years of physics trying to figure out if the universe oscillates, like this is the current oscillation. Because our universe is expanding, it doesn't look like the oscillatory models would work. they said, well, maybe the universe is part of a multiverse. So that's a possibility. Because of inflation, this breaks physics. So it breaks our physics from this point forward, okay? We have physics here. When we call natural physics, the physics of our objects that we measure now, this is unnatural physics. What is this? Okay. And so we don't know. And so you can have, this is where you even split into materialists and religious folks. And so Baha'i and Muslim and Christian and Judaism would say that would be the creation event. Naturalistic physicists would say this is a multiverse. And then we have multiple multiverses, multiple universes popping into existence. And so this gets to what we call metaphysics and how you explain something that's outside of natural physics. And so that's a conversation for a different time. But just talking about this expansion, let's look at this accelerated expansion. Okay. Because that's where our term symbols come into play in our atomic spectroscopy. So you can measure this cosmological redshift. If you look at these spectral lines of the different stars, you can look at that sodium line. And so let's focus on that sodium line. It's one of the brightest, or I would say the darkest lines in these solar spectra. And if you look at a star that's further away than our star from us, we see that sodium line has moved more into the orange region. Okay. And how do we know it's the sodium line? Because it's a doublet. Okay, and we know that it's that doublet P1/2 and doublet P3/2, and it's shifting smoothly. If we look at stars that are the same kind of star as our sun, their brightness is associated with their distance, and we can confirm that in our in our own galaxy by parallax. So if we take a spectrum of this, or a picture of the night sky from, say, spring and fall, then we're at opposite ends of our orbit. And we can see parallax. In other words, the stars kind of shift, and we can get a 3D picture of stars that are nearby. And that's cool. We can say this star is close, that star's far, because we've got binocular vision by spring and fall, or winter and summer. And we can look at the sky at orbital parallax, and we can get kind of a 3D picture. That only really works for stars that are kind of close in our own galaxy. But we can say distance matches the brightness of these types of stars. So we have a kind of a distance scale based on brightness. And then we can look at that distance scale and look at the sodium line shift, and we say, wow, this red shift is also a distance measure. So we can do redshift. Now redshift we can measure far away, where we can't use parallax. So we match the parallax with the redshift in nearby stars, and then we use that redshift to tell us the distance of stars far away. And so this Z, this cosmological redshift, is the observed wavelength minus I would say the Earth wavelength divided by the Earth wavelength. So this is the sodium Earth wavelengths that we would measure right here in the lab, 589.6 nanometers and 589 nanometers. And then at this star far away, it would be 592 and 591.8. And so we could calculate that Z value. And this Z value then can give us a velocity of expansion. So the speed of light times Z will give us the velocity of the expansion of the universe. And so this star is moving away from us at 1,425 kilometers per second. Woo! That's fast. That's a lot of kilometers, but we're a long way away. And so we're really, we can see that effect far away. Now we can take that and if we measure this velocity versus distance, it's a linear relationship. And so this, like I said, the near distances match this orbital parallax, which is sort of the 3D vision using our orbit as our two eyes. And it tells us that brightness is distance. And look how linear it is. It's amazing. So the redshift is on the y-axis and the distance is on the x-axis. We use the orbital parallax to kind of set up this linear relationship here. And then as they get further and further out, that orbital parallax is more difficult to follow. And so then we use this distance using brightness. So brightness is used here for the x-axis, and then the observed minus Earth wavelengths is used for this axis, and it's pretty linear. And you say, well, wait a second, that's not exactly linear. Look at that cluster right in the middle. Okay, well, that's a galaxy. And we're looking at a galaxy, and those stars that are moving away from us as that galaxy rotates are moving away faster because they're rotating a center black hole. And those that are on the other side of the galaxy appear to be closer because they're coming towards us. And so there's that cluster right there in the middle is actually sort of kind of measuring. Now we can measure the rotation speed of that galaxy and its distance. It's pretty cool. Yes? Oh, yeah, megaparsecs. Very good. So this distance is really a long distance. And so we use a new term from Star Trek, parsecs. Okay. And even Star Wars too uses it. And it's 3.26 million light years. So that's a pretty big distance. And so here's the Hubble constant, this linear relationship, the slope of this line here that relates that redshift to the distance is Hubble's constant after Edwin Hubble, who confirmed the redshift. So Einstein's standard model of light and matter predicted that there would be this expanding universe. And Edwin Hubble was the first to identify the redshift. Like he said, oh, look at this sodium doublet. It moves. And the farther away the stars are, the more it moves. And so he confirmed that. And so the Hubble telescope, the Hubble constant, they're all named after Hubble. And so that parsec is 3.26 light years. And so a megaparsec is a million of those. So then we could use this redshift and Hubble's constant to get a distance for these stars. So let's practice on one. Let's do a calculation. So if we pick that one at 20 megaparsecs away, what would be the observed wavelength of the sodium line from that star? So we know that the Earth wavelength is 589.6 nanometers for the strong line. Where would it be? So we have all of these constants that we know. We know the Earth wavelength. That's this one. We know the speed of light. We know the Hubble constant, and we want to solve for this. And we know it's 20 megaparsecs. And so again, it's all about the units. We solve this equation, so we got to make sure that we use the speed of light in kilometers per second so that we can cancel that kilometers per second in the Hubble constant. We know our star is 20 megaparsecs away, and that megaparsecs cancels with the Hubble constant. So it's a pretty simple calculation if you follow the units, and we end up with 592.4 nanometers. Okay. And then lastly, when did that light that we just detected leave that star? So again, these are measured in light years, and so we can measure how long it took for that light to get here. So 20 megaparsecs is 20 parsecs, 20 million parsecs. And so this is how long it took that light to reach us, which just kind of breaks my brain. We make a measurement today of that light, and it left that star 65 million years ago and traveled in a straight line until it hit my tiny little detector on Earth. It's just bizarre to me to think about that even the light we see hitting that building over there from our sun left the sun 8 minutes ago. It's crazy. Now, there was always this thought experiment. What happens if the sun just disappeared and we lost the gravitational pull of the sun? I mean, we would not be orbiting anymore. We would go off in a tangent direction and everything would be dramatically different. It would be cataclysmic, okay? Would we know instantly, or would it take 8 minutes for us to figure that out? Right? And what that is the question, does gravity travel at the speed of light? It's like, what do you mean by gravity traveling? Does gravity have waves? Does gravity behave like a wave? I mean, matter behaves like a wave. We learned that in the particle in a box and in this quantum mechanics. Light behaves like a wave. Is gravity like light? Gravity's weird because it doesn't have a negative, right? We have a positive electric field. We also have a negative. We have a north of a magnet. We also have a south of a magnet. We have gravity, but is there an anti-gravity? Don't know. But isn't that weird? Every kind of force has an anti-force. You have a positive electron, you have an anti-electron. That's weird, isn't it? And so they set up these gravitational detectors. Yes? Pardon? Yeah, there's antiprotons too. Yeah. They made anti-hydrogen, actually. They made an anti-electron orbiting an anti-proton. So it's pretty crazy. Yeah. Okay, we get into energy transfer and changing of particle identities in the spring. So if you're interested in that, take thermodynamics, okay? You don't have to change your major to take that course. It could be a science elective. It'd be a beefy one, but it'd be good. Now, it is a lab, okay, but it's not a writing component. Okay, so you don't have to write these long reports. It's more like a worksheet. You know, you do the lab, you answer some discussion questions and things like that. And so, yeah, so thermodynamics, that's a big ad for my class in the spring, okay, where we get to talk about nuclear energy at the last part of the course. But since we're talking about stars and stuff, this is a great time to talk about nuclear. Well, let's see, LIGO. Someone quickly Google on your phone LIGO. I forget what it stands for. It's the Interferometric Gravity Observatory, but I forget what the L stands for. But they set up this this interferometer, right? We talked about interferometers when we were talking about infrared spectroscopy, and it depends upon the length, the mirror distance for light traveling, right? And so they have lasers in this interferometer that can measure the differences in distance between these objects that are made out of concrete. So it's not going to change its dimension unless something happens to gravity. And so they set one up in Spain, I think, and they set one up, did you find it?
It's laser interferometer.
Laser interferometer. Okay, so I forget the L for laser. So they have them in a couple of different places on the planet, and sure enough, they're waiting for a gravity event. You want to talk about faith? They built this experiment not knowing if anything would even happen. They're like, let's build these, and maybe something will happen. Okay, and sure enough, two black holes that were orbiting each other got faster and faster and faster, and then merged. And so they could detect this oscillation in gravity, and then all of a sudden, boom, they had this gravity wave as their mass doubled. And that gravity wave went through both of these interferometers at the speed of light. And so they're like, boom, we know. Now we know gravity travels at the speed of light. And so that's pretty cool. Yeah. So now we know if the sun disappeared, it'd take 8 minutes for us to realize it. Okay. Both the light would disappear and we would go flying off into space. And it'd be bad. Okay, so how many meters of this? How many meters is this star away from us? Okay, so then you just take the light years, and you convert it into meters using the speed of light, and so boom, that's a long way away. And it's 6.1 times 10 to the 23rd meters. That's pretty crazy. That's 20 megaparsecs. Just coincidentally happens to be a mole of meters away. Okay, so. Anyway, and so how long does it take you at the speed of light to traverse a mole of meters? 65 million years. That kind of maybe gives you an idea how big a mole is. Yeah, so that's kind of amazing. So this has been kind of just a gee whiz lecture. You can look up these videos that I have in the notes for your more information on this. It's pretty cool. And so this definitely is evidence for an ancient universe. So what confidence do we have that physics was the same 65 million years ago? Again, this topic of the course right now, spin-orbit coupling, because that sodium doublet is the same sodium doublet it is in that 20 megaparsec star so far away. And so that doublet comes from the magnetic coupling constant for the electron, and it's the same for that sodium atom as it is for the one on Earth, and the magnetogyric ratio, this G, and the magnetic field of that little electron. And so the splitting and relative intensities have not changed. The relative intensities are governed by Boltzmann's distribution. And so Boltzmann's distribution depends upon Boltzmann's constant. So it looks like that constant was the same in that star far away as it is on Earth. And so again, that star far away, it took 65 million years for that light to get to us, and it had the same Boltzmann constant and the same magnetogyric ratio. Okay, and so pretty interesting stuff to think about. So that's that sodium doublet. And then you can see the magnesium triplet, and you can see all kinds of other atomic signatures in these stellar spectroscopy results. So that's it for this lecture. I just thought it would be interesting to take our idea of atomic spectroscopy and look out at the stars. So see you next time.